Let's see. I forgot my mouse. So I'm having to learn how to keep this trackpad. Okay. The intent of this is to get you prepared for amateur radio technician class exam. So we're essentially going to review the answer to all 407 questions. It's, I guess, loosely based on Dan Romanchik's book, the No Nonsense Technician Class Study Guide. He has one for each of the classes. And the main thing that I liked about his is he restructures it differently than the ARRL manuals. And then he starts with sort of the basics about electronics and stuff before you get into operating procedures and rules and regulations, which seems to make a little more sense to me.
I would disagree.
Okay.
And the reason I would disagree is we know that the rules and regulations do not necessarily make sense. Okay, because they're legislative.
Right.
And that means it's a more difficult thing to learn.
True.
And if you get the hard things out of the way first, okay, it makes life easier the rest of the way.
Well, that's a viewpoint.
It's like when I was learning landing, the instructor said, we got a good crosswind today. I think this would be a good day to do landings. And we had near maximum crosswind. We did our crosswind landings. Risk landings were easy.
Huh.
So I don't know whether he wanted to play with the possible ground group or not, but that's what we did.
Sounds like as my instructor, you're flying along and he's got a switch somewhere and he turns the ignition off.
Nice.
And then watches you. I almost landed in the cornfield. And then he showed me how to hop the fence and start the engine. Anyway, it's sponsored by the Indian River Amateur Radio Club and the KSC Amateur Radio Club. That's the two closest to this area. There's also the Platinum Coast Club in Melbourne, which is, I guess, right now probably the biggest definitely in this county.
Yeah.
We'll have 5 approximately 3-hour sessions. Depends on, could be 2, could be 4. There's no cost for this. We tried out at with KSC Club to charge a $15 fee up front for taking the exam to sort of get some skin in the game, make people show up. It didn't seem to make any difference. So we're not doing, and the ARRL doesn't want you to charge unless it's for something like that, where it's not for the course. Now this worked last night.
Blinking this morning. That PowerPoint?
No, it's LibreOffice, but
Probably just an arrow down on your keyboard to do it. Your space bar. Either one, yeah. Lever.
I have to really do it the hard way. Okay, so I guess the question is, why do you want to get an amateur radio license? What can you do with it? There's sort of tons of things. I'm still learning about them. There's lots of contests going on almost all the time. There's what they call QRP. We have our QRP representative Viren here, which stands for low power, with typically 5 watts
Yeah, 5
People-
watts for.
Some people do 100.
Well, that'd be, low power, not QRP.
Okay,
QRP is 5 watts for digital modes like CW, RTTY, stuff like that. For sideband, it's 10 watts if it's phone.
okay.
But, yeah, generally 5 watts. Why would anyone do that?
Which?
QRP. You
Because
can do 1,500 watts. Why bother with QRP?
because it's a challenge.
Ooh, there you go. It's a challenge.
It may not interest some people. Some people may want to go 1,500 watts with stacked Yagis and
Yeah. I don't have to get contacts unless I do QRP.
okay. There's also what they call field days. There's one of those coming up in a couple weeks. I guess the Indian River Club is going to have it at the church.
Yeah.
Okay. The NASA Club, it looks like, and they haven't decided, is going to be out at Cars Park because there's a building with a nice covered porch and air conditioning and a restroom. There's connections to space station and other satellites that you can do. And you can do that as a technician. There's POTA, SOTA, LOTA, ILLW, NOTA, VOTA, and others. Stands for Parks on the Air, where people will go out and activate a park. So if you go to a national park that has a number, I've never actually done it, but I've contacted some people. You can activate it with that number and, get points, I guess, for POTA stuff. There's summits on the air where you go out to some tall hill. I don't know if that has to be registered or not as a summit.
I think they are registered because I don't think there's anything in Florida.
No, I wouldn't.
Yeah,
Mount Dora, maybe,
yeah, I don't.
but that's like 500 feet or something.
Yeah.
And LOTA, which is Lighthouse on the Air. And there's also the International Lighthouse and Lightships Weekend, which the NASA Club participates in at the Cape Canaveral Lighthouse. There's
Islands on the Air.
Islands on the Air. I didn't list that one. I'm trying to remember what NOTA is. Oh, NASA on the Air, which is going on right now. And then there's VOTA, which is Volunteers on the Air, which is a year long you get points for contacting ARRL volunteer members. So in my case, you get 10 points because I'm an instructor and a examiner. So you get 5 points each. If you get somebody that's one of the directors or somewhere in management, you maybe get 100, 150 points. A lot of people just like to build equipment, get into building antennas, which is a whole nother ball of wax.
AU0R.
There's public service where there's emergency communications, and there's 2 organizations, ARES and RACES. ARES is the ARRL, Emergency Communications, using amateur radio. RACES is similar but connected with civil defense, FEMA. There's local repeaters that you can access as a technician, because most repeaters are in the 2 meter, 70 centimeter band on FM or digital voice. There's nets that you can participate in. There's probably one every night around here. And then there's the digital voice, which is newer stuff, D-Star, DMR, Fusion, which allows you to connect to a repeater that's connected to the internet, so you can get to a repeater basically anywhere in the world. So you can talk on handy-talkie to somebody in Japan.
Is Mars
Yep.
still operating?
Mars?
I don't know anything about Mars, but I'm sure Byron does.
Mars, the military amateur radio service. We do have a local representative, Ron Jubowski, if I remember correctly. You do need radio that has been modified to operate outside of amateur bands in the Mars area. Most major retailers will do that work for you when you buy the radio, do the modification. If you're reasonably handy with electronics, it's usually pretty simple. You can just remove resistor, remove capacitor, something like that, and then that opens up the radio. And then with Mars, they will give you some cryptographic software that you get to use. So that is the only time as an amateur that you're allowed to legally do encryption. It's when you're doing Mars.
I didn't know that. Okay, let's talk a little bit about the exam for the technician class. We call it Element 2. Element 1 was for novice, which has gone away. There will be 35 multiple choice questions, A, B, C, and D. You need to get 74% or 26 correct, or miss less than 9 or less. They get the questions out of a question pool, which is 407 questions. There's 10 sub-elements. In other words, 10 different areas like electronic principles, which is the first one we'll talk about today. And then practical electronics, where it's schematics and parts and stuff like that. So it's broken up into 10 of those sub-elements. Each of those sub-elements will have anywhere from 2 to 6 groups of questions, and you get 1 question out of each group. So there's 35 groups altogether. You get 1 question out of each one. So you need to be able to get around 85, 90% on each group in order to ensure that you pass with a fairly decent score, although it really doesn't matter as long as you pass. When you take the exam, the first thing you need to do is apply for an FRN number. I'm trying to remember what it stands for besides Federal Resource or something number. You go to the FCC site and just fill out the form. There's no charge for it. And you need to do that for most of the licenses. If you're interested in GMRS or the FRS, Family Radio, those also require an FRN number. You will need your ID, like a driver's license, for the test. That's one of the things the examiners will check to make sure that your ID correlates to what you fill out on the 605 form. You need to bring 2 pencils. You can bring a calculator. You have to show that the memory is cleared. The TI 30 Roman numeral 2S or whatever, sort of the recommended one. They're about $14 at Walmart. For the technician, it's unlikely that you'll need the calculator unless you just can't multiply 2 times 10. You can't bring any notes. If you need to write stuff down, do calculations, you have to do it on the back of the answer sheet. Most important is read the question carefully, because sometimes the way they're worded, they will confuse you. And also read all 4 answers before you pick one, because you may see answer A that looks like it's right, but it may actually be answer D, which is all of the above. So you can get in trouble by not reading all four of them. And I've seen a lot of people that tend to go back when they're done and keep going through them again and changing answers. Not a good idea.
I'm gonna be positive.
And sometimes all of these choices are correct is the correct answer. That's why you need to look at them all.
We used to say RTFQ. Read the effing question.
Yeah.
It's easy to skip over one word.
And the best thing to do is take practice exams. This is a list of a lot of sites where they offer them. They're all free. Even the one on the ARRL site. The hamstudy.org, most people think is the best one out there because when you miss questions, it tends to ask you questions about that topic. It puts more of them in the practice exam. Any questions on those?
Didn't one of those organizations shut down?
I am hearing that the hamstudy.org, the guy that does it is retiring.
Yeah.
So it's not clear if somebody else is going to pick it up or what. But the others work.
Yeah.
And you can download the question pool. In fact, if anybody wants it, I can email them a copy and just go through the questions yourself and practice. I did that for my extra and just had my wife ask me the questions out of the question pool. Okay. Now, I don't know why that's there. It seems to be in the way of things.
Bill Gates.
Navigating with your finger is a problem. There we go. Okay. The first sub-element we're going to do is electrical principles. It's sub-element 5. There's 4 groups of questions and accounts for 52 questions out of the pool. So this sub-element will be 4 points on the exam. So first, we'll talk a little about some of the units and terms we're going to use. This one doesn't come up too much, but there's charge, which those that were in the basic electronics course, we talked a lot about charge and how that's what actually electricity is the movement of charge due to a potential difference through a conductor. And we measure that in coulombs. There's something like 6.24 times 10 to the 18th of those elementary charges in a coulomb. That one you don't really need to remember. Then we have current, which is the movement of the charge, and how we measure it is in amperes, named after a French scientist. I think it was James Ampere. And it's actually measuring coulombs per second. 1 coulomb per second is 1 ampere. Then we have the force that's required to make the charge move, or the potential difference, which a lot of times is called electromotive force, which is why we use the E to represent it. And we measure that in volts after another scientist named Volta. then the other basic component is resistance, which is the opposition to current flow. So we have a voltage which is trying to force current to flow and current flowing, but we have resistance which opposes the current flow. So the higher that resistance is, the less current you're going to get to flow for a given electromotive force. And we measure that in ohms, once again, named after a scientist named Ohm. He was a German. We have direct current and alternating current. Direct current only flows in one direction from the positive potential to the negative potential. We have alternating current, which reverses direction and it flows from positive to negative, negative to positive. It's not the same as going from positive to zero and back. That would be pulsing DC. It has to actually change polarity to be alternating current. Okay, we have conductors, which are what we use to flow the current through and how we connect things up. We have the opposite of a conductor, which is an insulator. Sometimes we call them dielectrics, depending on how we're using them. And they oppose current flow. In other words, they have extremely high resistance, no free electrons. Okay, so Benjamin Franklin discovered lots of things, and he's kind of responsible for our conventional current flow, which at the time, they didn't really understand what was inside of an electron. I'm not sure that we do today, but we have better models. So the theory is that electrons, or the charge on electrons, moves from negative to positive, but he defined conventional current flow as going positive to negative, which is what we normally use when we talk about circuits, not electron flow or charge flow. Like I said, direct current always in one direction, positive to negative, or high potential to low potential. And alternating just does just that. It alternates direction from positive to negative and back. Okay, voltage or electromotive force or electric potential is what causes current to flow. It's kind of like, if you think about the water analogy, it's like a high pressure pump causes water to flow through the pipe. And we call the current I and the resistance R, and we'll talk about those in a minute. There's typical little circuits showing current flowing through the resistor from a battery. And okay, so the first real question that will be maybe on the test: what's the electrical term for the force that causes electron flow? You're going to go with A. Anybody else got A?
Yeah, I'll go with that.
We haven't talked about it yet.
It's A, voltage. Okay. Direct current and the flow of electrons in a circuit. We use I for current. And conventional current flows positive to negative, which we talked about, as opposed to electron flow, which is in the opposite direction. And we measure it in amperes. Again, that same little circuit showing current flowing, and we label it I and measure it in amperes. So what is the name for the flow of electrons in an electric circuit?
D current.
Say that again?
D current.
We'll get them on.
Current. Electrical current is measured in which of the following units?
Amps.
We go with that French guy.
The French guy, yep.
You guys did schematics once.
Did I back up? We already talked about that one. I guess the only thing there is about batteries are supplying direct current. As opposed to some alternating power source, which could be a generator or some AC supply. And alternating current is one of the things that you have, your house power is alternating current. Typically in the United States, it's 120 volts. You may have a 240 volt outlet. You do have 240 for things like ranges or dryers. Other than that, it's not too, or air conditioning, not too common as a normal outlet. However, if you are one of the people Byron was talking about, it's got a 1500 watt RF linear amplifier, you're going to need a 240 volt outlet to plug it into.
Somebody decided they were gonna put a hot tub in my backyard and never did. It was just terminated. So when I did a rental, turned that off, plenty of coil, put it up in the attic and just left it. So ready to go.
Okay. AC waveforms are typically sinusoidal. You may see some distortion, but they're normally basically a sine wave. Things like triangle and sawtooth, square waves are sort of special purpose that you'll see in electronics. You're not likely to see that on your AC outlet at your house. AC is not always balanced. In other words, it doesn't always go to the same of voltage on either side. They could have some DC offset, but as long as it crosses the zero line and changes polarity, it would be AC. And a positive voltage is going to require a positive current. Negative voltage will induce a negative current. Okay, which of the following describes alternating current?
I'll take Charlie.
Aaron?
Between positive and negative.
Okay. Okay, frequency is another component of alternating current. The frequency of a direct current would be 0 hertz. In alternating current, frequency is a measure of how many times per second a waveform changes polarity. And we represent that in hertz. I believe he was another German. And that's why it's capitalized, which is important because it comes up in a question. Period is the inverse of the frequency. In other words, it's how long it takes for that waveform to change polarity. So it's a reciprocal relationship between frequency and period. So in the time domain, we look at how long it takes. In the frequency domain, we're looking at the frequency of it and where it would show up in the spectrum, which getting a little ahead. What describes the number of times per second that an alternating current makes a complete cycle?
D.
Okay. What's the unit of frequency?
A.
I started with the rental car. You got it.
Did I hear a or B?
Alpha.
That's Aaron.
Okay, Resistance opposes the flow of all types of current, whether it's DC or AC or RF, which we'll talk about later. It's not frequency dependent. We measure it in ohms. Sometimes we use the Greek letter omega to represent it. Again, the typical circuit showing current flow through the resistor. What are the units of electrical resistance?
Ooh.
C.
Never seen what?
B.
Really?
Mega who?
Mohs.
Oh, Mo's.
That's
Yeah. Mohs, for some reason, is out of date. If he, A, okay, A, Siemens is the reciprocal of ohms. It used to be Mohs, which was ohms spelled backwards. And for some reason, they decided to name it because they always got to name things after somebody. So it changed to Siemens some time ago.
Mo sounds better.
What type of current flow is opposed by resistance?
D.
Everybody getting those.
All the above. Ooh, okay, conductors. We use metal as a conductor because it has a lot of what we call free electrons. We talked about that in the basic electronics course, where they're what they call valence electrons. They're on the outer shell, and usually there's only one or two, maybe three. So they're very easy to be knocked out of the shell and can migrate to another atom. And they take that charge with them and leave a hole.
Is that legal migration?
Yeah. It's documented. And that's what the two pictures are showing when you apply a potential. And the one on the right is actually showing electron flow, because if you're familiar with a 9-volt battery, the black wire is going to the positive terminal.
Why are electrons green?
Because the sky is blue, so they had to be different, I guess. But essentially, we use metals because of the free electrons, so the charge can migrate from atom to atom when you apply some potential difference. Different conductors or metals have a different amount of resistivity because they'll have some resistance, but they're very low, so they will allow current flow as opposed to an insulator, which we'll get to. This is some of the resistivity ratings for silver, copper, gold, aluminum, mercury.
What, no steel?
Hmm?
You didn't put steel in there?
No, I ran out of room.
Okay.
But you can see that silver is by far the best conductor with the lowest resistance per foot, per 100 feet, however you want to measure it. They do it in ohm meters, which confuses me, but that's sort of the standard resistivity measurement. The dollar signs are sort of indicating the relative cost. So that's why we don't use silver very much, because it is quite a bit more expensive, or at least it used to be. Although copper, I think, is catching up. And gold is not as good a conductor, but we use it for things where, like connector fingers on circuit boards, things like that, where you want to prevent oxidation, where silver oxidizes quickly and copper will also do it. So usually copper on some sort of connector is plated with nickel or something to prevent that. And that's why we primarily use copper for most all connections and use a little lead and tin to fasten it together called solder. Why are metals generally good conductors of electricity?
B.
Yep, free electrons.
How can they be free if they're forced to flow?
Well, no, they're not forced. They are attracted.
They're attracted.
I think they're forced.
It's their own self-will to jump.
No, they have to force them to flow.
No, you provide an incentive.
Yeah, make the environment correct.
It's different when they're in the ionosphere and ultraviolet knocks them out.
Again, they're being forced.
They're being forced there. Okay, insulators are nonmetals, and if you look at the periodic chart, they're kind of all together. Sometimes we call these dielectrics, like when it's used for insulation on wire, or if it's the insulator within a capacitor. Typically, most plastics, glasses, things like quartz, even silicon is an insulator, even though it's used in semiconductors because we add some impurities, so it's no longer an insulator. But glass is the one that's highlighted because it's the one that will be on the test. This is a little comparison between conductors and insulators. Conductors will have 1 to 3 valence electrons, and insulators will have almost a complete outer shell, 5 to 8. So it's very hard to move those electrons out of the valence shell.
If there's 4 electrons in the valence shell, does that mean it's a transgender atom or element? Transitioning.
Yeah, it could be a trans. There's a term, and I had to look it up to see what it really meant because it's very confusing. The electronegativity, which is sort of the opposite of what it sounds like. Low electronegativity basically means it's a good conductor. I think it means that it doesn't retain electrons easily, where high electronegativity means that it does. Anyway, the good conductors are silver, copper, gold, aluminum, and insulators are mica, glass, rubber, plastic, etc. Which of the following is a good electrical insulator?
B.
Unless it's lined with mercury.
Glass. The others are all conductors.
Mm-hmm.
Copper, aluminum, even mercury, which is why I added mercury to that other chart. Even though it's not a very good conductor, but it's in batteries.
But it makes a good switch to the old time.
Yeah.
Stats.
Right. Okay, Ohm's law. Now, the sort of official definition is for an ohm is an electrical resistance between 2 points of a conductor when a constant potential difference of 1 volt applied to those points produces in the conductor a current of 1 ampere. And they go on the current not being the seat of any electromotive force, which means there's no battery in that section of the conductor. Ohm, another scientist, discovered that phenomena of resistance, and he came up with what's called Ohm's law, where the resistance in ohms is the ratio of the voltage to the current, or the potential to the current. And he derived it by just plotting current and voltage on different through different substances. And on most materials, it turned out to plot a straight line, and the slope of that line, which is that ratio of potential to current, turns out to be what they call resistance in ohms. So it's really measuring the slope of the line. And like I said before, we use the Greek symbol omega. Sometimes you'll see that on schematics and things, or in technical writing. Here's an example of a plot I did just to show where R is the slope of that line, where we applied voltages up to 25 volts and we got 2.5 amps. So therefore the resistance was 10 ohms. And it came from the basic, I guess, first order formula of Y equals mx plus B, where B is the Y-intercept point where it would cross the Y-axis. So in this case, it would be 0. So it's this Y is equal to mx, or E equal IR when you put it in different variables. Here's the little cheat sheet, which a lot of people use, in which they teach in order to remember Ohm's law, where you put your finger over whichever one of those three variables that you want to solve for. So if we put our finger over the E, saying we want to know what the voltage is, then we would multiply I, the current, times the resistance, which is what the vertical bar is indicating. If we wanted to find current, then we would divide E by R. If we wanted to find resistance, we would divide E by I. So if you have trouble with Ohm's law, you can try to remember the little circle and write it down on the back of your answer sheet. And you can get any one of the three formulas. I showed some example calculations there for finding voltage, current, or resistance. It just takes a little practice, pretty simple. What formula is used to calculate voltage in a circuit? Anybody out there?
A.
Sounds good. What formula is used to calculate resistance?
B.
What formula is used to calculate current? Guess you didn't see that one coming.
B.
What is the resistance of a circuit in which a current of 3 amperes flows when connected to 90 volts? So you know current and you know voltage. What's the resistance?
I think B, Alex. Yeah.
Any answers out there?
B.
Good job. R is equal to E divided by I. What is the resistance of a circuit in which the applied voltage is 12 volts, the current is 1.5 amperes? Same question, different values.
18.
C.
What did you say, Byron?
I said, A, someone said, C.
Well, someone got it right.
What? Hold on, let me see. Yeah.
12 divided by 1.5.
Oh,
Read the question carefully.
That's okay, I'll do it slightly this way.
What is the resistance of a circuit that draws 4 amps from a 12-volt source?
A.
And we'll resistance on this one.
Oh, my goodness. Yeah. I'll go A this time.
yeah, A. Right.
Okay. What is the current in a circuit with an applied voltage of 120 volts and a resistance of 80 ohms?
25, 80.
A.
Yeah.
A, because that's the magnitude. 2 zeros, yep.
What do you say?
A, public now, I'll go with D.
You're not doing good, Byron.
Yeah.
This is the light bulb, basically.
Voltage. Yeah. Oh,
Read the question carefully. What is the current through a 100 ohm resistor when connected across 200 volts? So we want I, we know E, and we know R. So remember, we want I, we know E up here and R down there. Okay. What is the current through a 24 ohm resistor when connected across 240 volts?
C.
Same problem, different numbers.
E.
Okay. Now you notice all of these have been group D, which means you only get one of these.
Mhm.
You just don't know which one. What is the voltage across a 2 ohm resistor if a current of 0.5 amperes flows through it? So we want E, we know R, we know I.
A.
Yeah.
What is the voltage across a 10 ohm resistor if a current of 1 amp flows through it? Okay. There's a lot of these. So you're almost guaranteed to get one of these Ohm's law questions.
Mm.
What's the voltage across a 10 ohm resistor if a current of 2 amps flows through it?
D.
Very good. Okay. Now we can put things in series or in parallel. So we'll talk about series and we'll just talk about resistors for now, because inductors and capacitors behave a little differently, and that's later on. The main thing on a series circuit is that the same current is going to flow through all the components. So in the little schematic there, where I put an ammeter showing the current through each one, they're the same. It's 1 amp through that circuit. Now, the voltage across each of those resistors may be different, which was E1 and E2, because the current is the same, but the resistance is different. So in other words, we'd have 1 amp through R2 at 5 ohms, so there's going to be 5-volt voltage drop. And we have 1 amp through R1, which is also 5 ohms, another 5 volt. It adds up to 10 volts. It must always add up. There's a law. One of Kirchhoff's laws that says the voltages around there will sum up to 0. So for simple series components with resistors, the current's the same through all of them, and the resistance values add up. So that total resistance is going to be R1 plus R2. In which type of circuit is DC current the same through all components? Parallel, okay? In parallel, the voltage will be the same across all the components. The currents will be different. So if I have, I've got a 10-volt supply, so I have 10 volts across R1, which is 2.5 ohms, so it's going to have 4 amps of current flowing through it. I've got 10 volts across R3, which I should have labeled R2, which has only got 2 amps flowing through it. Okay, but the voltage is the same on each one. The currents are different. And in this case, the currents would add, so we have 6 amps coming out of our supply at 10 volts. In which type of circuit is the voltage the same across all components? Parallel. Okay, DC power. We got another little pie chart, and this one spells pi, where power is current times voltage. It's part of Watt's law, a Scottish inventor famous for the steam engine, but he also did a lot of work with power. And he has a Watt's law formula which relates watts to joules of energy. In our case, power is equal to voltage times the current. So you use the little pie chart the same way. You put your finger over the one you want to solve for, and you either multiply or divide depending on which one it is. Fairly straightforward. Any questions on power? It's just like Ohm's law. I want to reorient them a little bit. There's an example where we have 13.8 volts, which is a typical DC battery voltage, which is if you buy an amateur radio base station or mobile unit, it's going to be specified to run at 13.8 volts, which means it'll be anywhere from 12 to 14, basically, or slightly over 14. In this case, I picked a 1.38 ohm resistor, so we have 10 amps of current flow. So the power is going to be the current times the resistance, which I multiplied wrong. Oh, no, I didn't. Because we hadn't got to resistance part yet. Ignore what I said. It's later, but it is 138 watts. Which term describes the rate at which electrical energy is used?
Ergs.
C.
That's a measure of it.
Yep. Electrical power is measured in which of the following units?
B.
Good old Watts.
Mhm.
Everything's named after somebody. What's the formula to calculate power in a DC circuit?
A.
How much power is delivered by a voltage of 13.8 volts and a current of 10 amps?
A.
Mhm.
How much power is delivered by a voltage of 12 volts and a current of 2.5 amps?
B.
How much power is delivered by a voltage of 12 volts and a current of excuse me. Current required to deliver 120 watts at a voltage of 12 volts. So we want current, we know watts and we know voltage.
B.
Okay. Now this stuff, a lot of people have trouble with. If you're not familiar with using these units, so we'll try to go over them. These are prefixes that are used so to make things easier instead of dealing with a whole lot of zeros. So we use the term milli to represent 1,000th of a quantity, or 10 to the minus 3. I think it comes from Latin for milli being 1,000, which is kind of the opposite of a kilo or kilometer is.
Nano.
One of the examples is we measure current in milliamps, which would be 0.001 ampere. In most electronics, we're dealing with less than an ampere. And we use the small m a lot of times to represent milli. Like I show there is 1 milliamp. A would be capitalized because it's proper name, ampere. We have a micro, which is a millionth of a quantity, or 10 to the minus 6. And we tend to deal with microvolts in receivers, represented as the 0.000001 volt. A lot of times we use the Greek symbol mu to represent that microvolt, or the micro symbol. It could be microamps. It could even be microhertz. Next is the pico, which is 1 trillionth of a quantity. And you notice each of these milli, micro, pico was a factor of 1,000 difference. So we have 1,000, a million, a billion, or excuse me, a trillion. I left nano out. That's why I'm not sure why I left that one out. Nano that you don't see, we represent with a small n, which is 10 to the minus 9th, or a billionth of a quantity. Pico is a trillionth, 10 to the minus 12th. And we use a small p to represent that.
Lyric's favorite, the femto.
The femto, yeah.
Yeah.
We don't deal with femtos in any of the licenses yet.
Yeah.
Okay. Okay, going the other way, we have kilo, which you notice is a small K. It makes it different. I'm not sure why, because it confuses people, which is why there's a question about it. It represents 1,000 quantity, or 10 to the third, if you're familiar with exponents. Kilovolt would be 1,000 volts. And we use a small K, capital V, because it's a name, volts, after volta.
I think the small K is because in mathematics, K, capital K is constant.
I'm not sure.
I
I haven't seen an explanation of why, except
think,
with word processors, if it's at the beginning of the line, it always wants to capitalize it and you have to go back and undo it. Mega is 1,000,000 or 10 to the sixth. A megahertz would be a capital M followed by a capital H, little z, because it's a name, hertz. That's why it's a capital H. And we have giga, or a billion of a quantity, or 10 to the ninth. Gigahertz, we won't talk about terahertz, which would be the next one at T. I guess amateurs have privileges at terahertz. I'm not sure what you have to do to get there. Almost getting into light. Here's a little table kind of showing them all together and the abbreviations, what the exponential representation is. The basic one to remember that confuses people is kilo is a small k. And they go up in order of thousands, either dividing or multiplying by 1,000 for each one of these. Some more examples of converting amperes to milliamperes. There's 1,000 milliamps in an amp. I find that's the easiest way to remember these things, is what that conversion factor is. A lot of people like to do, well, you move the zero so many places left or right. That confuses me more than just knowing how many of a quantity is in the other quantity. So in hertz to kilohertz, there's 1,000 hertz in a kilohertz. Microvolts to volts, there's 1,000,000 microvolts in a volt. In milliwatts to watts, 1,000 milliwatts per watt. Megahertz to kilohertz, there's 1,000 kilohertz in a megahertz. And ohms to kiloohms, there's 1,000 ohms in a kiloohm. That covers most of the ones on the test. So how many milliamperes is 1.5 amperes?
1,500.
Any guesses out there? Aaron?
Oh, sorry, I was on mute. D.
Any guesses?
Roger's making coffee. That's why I'm not answering.
Oh. Okay, 1,500 milliamps in 1.5 amperes. Which is equal to 1,500,000 hertz. Any answers out there?
A.
Okay. which is equal to 1 kilovolt.
C.
Okay. Which is equal to 1 microvolt.
A.
Hey. Micro's a million. Which is equal to 500 milliwatts.
B.
Good. Which is equal to 3,000 milliamperes. Did you say? Oh,
But I'm doing public now. Delta. I'll stick phonetically.
D, 3 amperes, 1,000 milliamps per amp. What is the abbreviation for kilohertz?
D.
Right. I noticed in their question, they didn't capitalize the H in kilohertz, which I think would be correct, but it's not my question. What is the abbreviation for megahertz?
D.
Good. Ooh. Which is equal to 3.525 megahertz. So they want the answer in kilohertz.
Charlie.
C.
Very good. Which is equal to 28,400 kilohertz. And they want the answer either in kilohertz or megahertz. They did that to confuse you.
Big delta. Well, I mean. A could be right if you just skipped over the term. I mean.
Yeah.
This.
That's why you need to read them all.
Only be off by back. D.
Okay. D it is. 28.4 megahertz. Which is equal to 2,425 megahertz. And they want it in gigahertz. Any answer out there?
C.
All right. Which is equal to 1 million picofarads. Remember, picofarads were 10 to the minus 12.
C.
Six.
And I made the mistake of not listing nano in the list, which would be 10 to the minus 9. And then we had micro, which was 10 to the minus 6. So the difference between micro and pico is 10 to the 6th, right? Or a million.
Mhm.
One microfarad. If you're in the moving the decimal point, you move it 6 places.
Yeah, well, that's the only one that's
That stuff confuses people, so don't feel bad if you're having a little
out
trouble.
of your answers. That's the only one that made sense, like
That's-
shifting the
yeah.
decimal.
That's the other thing about the test. Most of the answers, particularly on the math type, there's only one that's going to be close. Okay, decibels. We use decibels to talk about ratios of items, particularly power, but it's also used for voltage and current. And it came from the AT&T sort of Bell Labs long distance transmission, and they came up with the bell to represent a measurement value, but it was too big for electronics. So we use a decibel, where a deci is a tenth. So it's a tenth of a bell. And it's a logarithmic representation on powers of 10. And the formula, if you see over on the right-hand side for power, which we will mostly talk about, would be 10 times the base 10 logarithm of a ratio of 2 powers. So if we had, for example, P2 in that formula was 100 watts, and P1 was 10 watts, then the ratio would be 10. So the log of base 10 of 10 is going to turn out to be 1, and we multiply it by 10, so it would be 10 dB. That's one of the ones that you kind of want to remember, are the 3, 6, and 10, and the -3, -6, and -10. If the ratio is less than 1, you get a negative number. So a 3 dB increase in something means the power has changed by a factor of 2. If it's 6 dB, the power has changed by a factor of 4. If it's 10 dB, it's changed by a factor of 10. Likewise, if it's 1/10 of the value, it's down or minus 10 dB. Usually when you see signal strengths, they'll be reported as typically a minus dB number. Now we tend to represent them relative to some value. In the case of antenna gain, you'll either see it as dBi or dBd. dBi is relative to the isotropic radiator, which is a theoretical antenna, point source antenna, or a dBd, which is relative to a dipole, which is theoretically 2.15 dBi. So you'll see it both ways, and they tend to use dBi because it gives them a bigger number for advertising purposes. Sometimes you'll see it voltage, and the difference is because of the square function which we didn't get into yet for voltage and current relative to power. It's going to be 20 times the log as opposed to 10. But the thing to remember, if it's a positive ratio, it's a plus dB or an increase. Negative is a decrease. Okay, which decibel value most closely represents the power increase from 5 watts to 10 watts?
B.
B, 3 dB. It's a ratio of 2 to 1. The log of 2 is 0.3. You don't have to remember that. And times 10, it's actually like 0.301 something. So it's not exactly 3. Which decibel value most closely represents a power decrease from 12 watts to 3 watts?
C.
Very good. Which decibel value most closely represents a power increase from 20 to 200 watts?
A.
Oh. Okay, time for a break. Tea or coffee or whatever. We'll pick it up in a couple minutes.
I have no good answer why it's not capital K. I thought capital K was, pretty common for, the constant, but it's not.
Yeah, I've never saw an explanation of why they went to the lowercase one, just to confuse people.
There's a.
Okay, so next we're going to talk about components and circuits. We'll cover 47 questions and there's 4 groups, so 4 of these will be on the test. We'll talk about resistors, capacitors, inductors, batteries, diodes, transistors, schematic diagrams, resonant or tuned circuits, and some other miscellaneous components like transformers, relays, fuses, etc. So first we'll talk about resistors, and we know that they oppose the flow of current for all forms of current. The picture on the right of typical modern day resistors without showing these little surface mounts, which would be hard to see, especially if you try to actually work with some. I've been able to do it, but with about a 10 power magnifier on my head. We specify them in ohms. They come in fixed or standard values, depending on the percentage of accuracy. Used to be 20%, 10, 5, and 1, and then you can get some even more precision than that, but they're rare. I don't see 20% much anymore. Those used to be the old carbon core resistors. Most of the newer ones are going to be 10 or 5. There's also a variable resistor. Sometimes we call it a potentiometer. It has 3 terminals instead of 2, where one is a wiper that moves along the resistance path, so it can vary the amount of resistance between one point and the wiper. And we use that when we're using all 3 leads. We typically call that a potentiometer because it's using a voltage divider, basically. If it's tied to one end, it's only varying the total amount of resistance. We use them in audio as a volume control. We use them in power supplies as a voltage control for a voltage regulator.
So there's what? 2 general flavors, linear and log linear or audio taper?
On the potentiometers, right, they're linear, and audio, I guess there's a log version of audio also.
I think the log and the audio may be the same thing.
Yeah. But that's not on the exam. It's just good to know. Okay. What electrical component opposes the flow of current in a DC circuit?
R.
B.
Very good. What type of component is often used as an adjustable volume control?
C.
See,
What electrical parameter is controlled by a potentiometer?
R.
B.
Okay, capacitors. A capacitor is two conductive surfaces separated by some form of insulator, which we call a dielectric. The amount of surface area and the separation determines the amount of capacitance. When we apply a voltage, a DC voltage, it charges the capacitor by making one plate positive, meaning it has atoms that are missing electrons or holes, and the other plate would be negative, means there's an excess of electrons. And it creates an electric field between those conductive surfaces or plates. That electric field can store energy. And the ability to store energy in that field is called capacitance. And we measure capacitance in farads, which I probably should have capitalized because it's another person, Michael Faraday. I think he was maybe American. Not sure.
I think he may have been European because
Yeah.
he was part of the
Probably.
Royal Society.
On the left is a little thing showing the field and the alignment of the charges in a capacitor made with two plates, where we have a positive charge on one and negative on the other. And that charge is equivalent to the amount of energy stored. Now, I did a little circuit with the resistor and capacitor, and it shows down there the input voltage, which is just a square wave, which goes up to 1 volt. And you see that the voltage across the capacitor, which is the yellow or gold line, slowly charges up to the input value. Okay, so it starts off when you apply a voltage to a capacitor that's discharged, it looks like 0 ohms initially. And then as it's fully charged, it will look like an open circuit or infinite ohms. Likewise, when we take the voltage away, it starts to discharge back through the resistor in this particular circuit. And the rate at that decay is called time constant, which we won't go into for the technician. But the values of R and C determine how fast that charges and discharges. But the basic thing to remember is it stores energy in the electric field, and it charges up slowly depending on the circuit. What type of electrical component consists of conductive surfaces separated by an insulator?
D.
Both that sauce together.
Well, it's involved in coal pits. What electrical component stores energy in an electric field?
B.
What describes the ability to store energy in an electric field? What is the unit of capacitance?
A,
Okay, inductors. We make inductors from a coil of wire. One or more turns, actually just a straight wire will have a little bit of inductance. As you coil it up, the magnetic fields tend to combine within the center. That magnetic field is caused by current passing through that conductor. And it stores energy in the magnetic field, similar to the way the capacitor stores energy in a electrostatic or electric field. And that ability is called inductance, to store energy in the magnetic field. And we measure that in henries, named after, it wasn't John Henry.
Ah,
Little diagram showing the magnetic lines of force and how they get concentrated in the center when you coil the wire up. And the more turns, the more that electric field is concentrated in the middle, and of course, the higher the inductance. Similar to a capacitor, where the area of the conductors and the distance determines the amount of capacitance. In the inductance, it's going to be the number of turns and the diameter of the coils to determine how much inductance and how much the energy is stored in the magnetic field. Here's a similar circuit with an inductor and sort of a capacitor and how it charges up. And you notice on the inductor, it looks like have extremely high resistance initially. So we see the full, in this case, 10 volts across it. And as that magnetic field charges up, the voltage will decrease down to zero. So it will have no current flow initially. And once it's charged up, it will have the maximum current flow depending on that resistor in the circuit. Because if it was a perfect inductor, it would have no resistance. So it would look like 0 ohms at a certain point in time. When you take the voltage away, I have that magnetic field in there that starts to discharge, and that actually causes a reverse polarity voltage as it discharges back, because you're putting that energy back into the circuit. If you have ever dealt with things like relays, where you apply a voltage to it, or actually any kind of inductive thing where you've got a switch and you're applying a voltage and taking it away, as that magnetic field collapses, it generates extremely high opposing voltages, which will actually cause sparks to jump over the contacts, which is why in most relays on their solenoids, you put a clamping diode in the opposite direction, so it shorts that voltage out and discharges the field. What electrical component is typically constructed as a coil of wire?
So,
B,
Delta. What type of electrical component stores energy in a magnetic field?
C,
What describes the ability to store energy in a magnetic field?
inductance.
D,
What's the unit of inductance?
C,
Okay, batteries. We have two types. We deal with rechargeable and non-rechargeable. Flashlight batteries are a common example of a non-rechargeable battery, even though they make rechargeable ones, but the standard carbon zinc battery can't be charged. This is a chemical reaction that goes on that's not reversible. And it's showing a little cutaway diagram of what's inside one of them. As a kid, we used to take them apart and get the carbon rod out of the middle. And then you could make a razor blade radio with that, winding a coil around it and using a safety pin and a razor blade. On the right is an example of a lithium battery. I think that's a lithium ion, but there's so many variations of lithium nowadays. But basically, it has an electrolyte in it, and it uses some lithium material as one of the elements. And then I think in this one, the one collector is made out of copper and aluminum on the other side, but essentially it's just a rechargeable battery. And the ones that we normally deal with on rechargeables are lead acid, your car battery, or in some cases, you may use it for emergency power to power up a base station and recharge it with solar cells. Nickel cadmium, which isn't as popular today, but they're still around. Lithium ions. Most of your handheld radios are going to have some form of lithium rechargeable battery in them. Nickel metal hydride is another one of the older ones. The non-rechargeables are going to be your carbon zinc, or your alkaline and mercury. Most of those are like the button cells that you see for watches and various small things. So which of the following battery chemistries is not rechargeable?
B.
Which of the following battery chemistries is rechargeable?
D.
Okay, diodes. It's your most basic semiconductor component. It's composed of two electrodes, an anode and a cathode. And we mark the cathode normally with a stripe, at least for the smaller diodes. As far as exams concerned, it's a stripe on the cathode. When they're forward biased, which means we have a positive current or positive voltage on the anode, they will conduct current from the anode to the cathode. When they're reverse biased, in other words, the opposite polarity, they will not conduct current unless you apply enough voltage to actually burn it up, and then it sort of becomes maybe a resistor, but it's no longer a diode. When you're passing current, it has a forward voltage drop, and that's dependent upon the type of material at the p-n junction. If it's a germanium diode, which aren't used as much anymore, but they're approximately 0.3 volts forward voltage drop. In other words, you have to get up to 0.3 volts before it will conduct. If it's made of silicon, it's approximately 0.7 volts before it conducts. And then we have a special, well, there's lots of variations of diodes, but the one on the exam, the other one is an LED or light emitting diode. When it is forward biased, it will emit visible light. That is, once you exceed its forward voltage drop. And because the materials are a little bit different for light emitting diodes, their forward voltage drops will be different. Not an exam question, but in some cases they're up maybe over a volt or more, depending on the type of material, and that determines the color. They're used as indicators in digital readouts.
They don't talk anymore about LCDs, kind of old technology.
General or extra,
Hmm.
not technician. Okay, the one on the left is showing the conventional current flow and electron flow or charge flow, and how it happens in that piece of semiconductor material, where when an atom loses its outer valence electron, it's called a hole. So there's a space there for an electron to jump into. So that's where the free electrons go. And while they're free and not attached to an atom, then it's a negative charge or a negative ion. When you've got an atom with a hole, it's a positive ion because it has a positive charge, because it has one more proton than it has electrons. Over on the right, showing the p-n junction for a diode, where there's a type of p-type material and n-type material fused together. And at that junction, called the depletion region, is where this magic stuff happens with the biasing and the conduction. It'll go from P to N, but not N to P. The symbol it's used to represent it is next, which is that filled in triangle with a stripe. And that is the cathode, which is what's represented on most diodes. It will have a stripe on one end, indicating that's the cathode or negative end. A little bit about P and N material. You take a piece of silicon, which is a crystal, which is normally a non-conductor, and they do different processes to embed impurities. So the major one is a boron impurity that they put and make a P-type material. And if you can look at the little crystal lattice there, you see that it creates a hole, which gives that material a positive charge because it's got extra holes because of the fact that the outer electrons are different. And when you grow the boron in the crystal lattice, it causes some electrons to be shared and you wind up with an empty spot, lots of empty spots. For N-type, they normally use phosphorus to do the same kind of thing, except you wind up with excess electrons, so it makes it negative charge. Now, they also use some other materials, but boron and phosphorus are the most common. Sometimes they use antimony, arsenic, other things that are in that funny section of the periodic table to do different things. But basically, they make one piece of silicon positively charged with holes in it, and the other one with extra electrons in it. Here I just did a simulation, and they have a perfect diode in the simulator, which is what the gold line is. And you see that at anything above 0 volts, it conducts. The slope of that line is the resistance value that's in series with it. The blue line represents a silicon typical semiconductor. I think it was 1N41, 48. And because of the curve, it's actually hard to say where they measure that because it could be anywhere from 0.6 to probably 0.7. But on the exam, they call it 0.7. I think when you get into the general or extra, they've gone back to 0.6. It's somewhere in that range. And you can also see that the slope of the blue line is slightly less than the gold line because that diode has some internal resistance. Okay, what electric component allows current to flow in only one direction?
I'll say
See.
Griffin.
What are the names for the electrodes in a diode?
C.
How is the cathode lead of a semiconductor diode often marked on the package? Did I hear a Baker? I guess it's Bravo, isn't it?
It's Bravo now.
You're talking aims of nuclear tests, yeah, Alpha Baker.
Which is true about forward voltage drop in a diode? Tricky one.
Well, A is true. Yeah.
We have any votes for alpha?
I'll go for Alpha.
See, they don't require you to know that it's 0.3 or 0.6 or 7, just that it's not the same. What causes a light emitting diode, an LED, to emit light?
Forward code. Okay.
Any alphas out there?
Yeah.
Which of the following is commonly used as a visual indicator?
A.
You need the Nixie tool.
Yeah. That's what.
Okay, transistors. It's another semiconductor component. This time we've added a third piece of material. So we have either a P, an N, and a P, or an N, a P, and an N. There's sort of two flavors. There's the bipolar, which were the first ones that were practical. I think they had a theory about the field effect, but they couldn't make it work initially. A bipolar junction transistor uses current on the middle or the base element to control current flow between the other two, in this case, the collector and emitter. In a field effect transistor, which has source, gate, and drain, the gate is the controlling element, and it's controlled by voltage because it uses an electrostatic field to control the amount of current that flows between the other two terminals. It turns out that most field effect transistors are symmetrical, so you can switch it around and use the drain as the source and vice versa. It doesn't make any real difference. Just an aside, not on the test. Can be used as a switch, either one of them, where you can have it conduct current as a very, very low resistance or appear as a very, very high resistance. Looks just like a switch. Can also be used as an amplifier where you can vary the output current or the current through it proportional to the input signal, which is a current or a voltage, depending on whether it's a bipolar or a field effect. And that ability is called gain in order to amplify an input signal. So you can typically have a gain up to, I don't know, maybe 100 for simple amplifier circuits. And the gain is the ratio of the output to the input. So if it's power gain, it's output power to input power. If it's voltage gain, it's output voltage versus input. Likewise for current. That's one of the things that we tend to measure in dB. Okay, for a bipolar, like I said, the current input on the base is what controls the current output. And if you look at the construction, we have our diode, which is that PN junction from base to emitter. And it works, it's a diode. It has the same forward voltage drop. If it's a silicon transistor, it's going to be 0.6 or 0.7 volts before it starts to conduct. When you have current flow from the base to emitter, it allows proportional current to flow between the collector and emitter. I'm not going to try to explain how that works because I don't totally understand it. But, you know, it gets into some of that quantum stuff. There are 3 electrodes called emitter, base, and collector. The schematic is there on the right. You see a little arrow on the emitter lead, and if it's an NPN resistor, which we're showing, that arrow is pointing towards the emitter. If it was a PNP, then the arrow would be in the opposite direction. It would still be on the emitter, but going into the substrate. Like I said, there's 2 types, a PNP and an NPN. NPN are the most commonly used, but sometimes you need a PNP because of the voltages you're dealing with. And they're just made from the same 2 types of material, and whether or not it's a PNP or an NPN layer. The field effect uses a voltage to control the output current, and that creates an electric field. And as you can see in the little diagram on the right, the field is between the gate and the body of it. And that controls the amount of current that can flow through that NPN junction that you see between source and drain, or drain and source. There's also 2 types, a P channel and an N channel. The symbols are down there on the bottom, and the arrow goes in or out depending on whether it's an NPN or a PNP. Like I said, they're gate, drain, and source. The gate is the controlling element. So they function just like the bipolar, except they use voltage on the controlling element to control it, as opposed to current through the controlling element.
Now that's what's base replaces the main diode for the front end on receivers.
Could be, yeah. Well, I mean, it is a diode. I mean, even there, you can get a diode effect. In fact, with the capacitance, I've seen them used as variable capacitors, just using the gate and source.
Oh,
Like a reverse diode, you can use it as a varactor. It appears as a capacitor. variable, voltage variable. Okay, which of these components can be used as an electronic switch?
C.
Yeah.
See.
I'll take-
You take C? All right, C's a winner. What's the term that describes a device's ability to amplify a signal?
A.
Which of the following can provide power gain?
Transformer.
Yeah. Now, the reason they worded it that way and said power gain, and they threw in transformer,
That's voltage.
because the transformer can't provide power gain, but it can provide voltage or current gain. Which of the following components can consist of three regions of semiconductor material?
B.
Just the look. Yep. Trios is that.
Well, it doesn't have semiconductor material in a triode, but it works just like a FET.
Mhm.
What are the names of the electrodes of a bipolar junction transistor?
B.
What does the abbreviation FET stand for?
Yeah.
D.
I mean, it's not a frequency emission transmitter.
Sounds good.
What type of transistor has a gate, drain, and source?
But
Bravo. Schematics. Okay, they're used to describe how a circuit works, how things are interconnected. It makes it easy to reproduce the circuit. They show the components. They show the interconnections. They tend to use standard symbols depending on what country you're in, which show the type of the component, sometimes, and usually the value of the component. Sometimes it may have part numbers for manufacturing purposes. Here's a typical little schematic. You see a title block. Usually they have that, indicates when it was drawn, what the item is. They may have a little parts list or something attached. It shows all the various pieces, how they're interconnected together. I think that happened to be an Arduino of some sort. What is the name of an electrical wiring diagram that uses standard component symbols?
yeah.
C.
Which of the following is accurately represented in electrical schematics?
C.
Yeah.
All right. Okay. Now these are coming up are actual diagrams that will be on the exam. So they ask questions about them. So in this picture, number one is a resistor. That's the squiggly representation of a resistor. Number two is a transistor. In this case, it's a bipolar junction transistor. Number three is a lamp, not an LED, but an actual incandescent lamp like a pilot light,
That little lightning bolts.
which you hardly see anymore, but yeah, they're still around, huh?
I was expecting an inductor in the lamp, but there's no inductor in there.
Yeah, there is. There's half a loop.
Half of it, okay.
And number four is a battery. Number five is one of the symbols for ground. Sometimes it's a triangle pointing down. So what is component one?
R.
Resistor. What is component two?
Well,
B.
What is the function of component two?
yeah.
I'll go with control the flow.
Right. Because in this circuit, that signal coming in through resistor one is going to turn that transistor on and light the light. What is component three?
C.
Yeah.
What is component four?
D.
Oh.
Okay. Another one. Here we show an AC power plug as number one, a fuse as number two. Sometimes the fuse will have a little sine wave in it showing the element. Number three is a single pole, single throw switch. And notice it just has two terminals and a lever or contact that moves, either connects it or disconnects it. Number four is a transformer. Number five is your diode. Number six is one of the representations for a capacitor. In some cases, whether it's an electrolytic or something, the symbol will vary slightly, but it will always be two plates separated. Number seven is another resistor. This shows that you can rotate them. Number eight is our LED, which is a diode with a couple arrows showing the light being emitted. Number nine is our variable resistor. And in that case, whether it's tied to one end, it's actually just a variable resistor, not a potentiometer. And number 10 is a Zener diode, which you notice the little on the cathode, sort of a Z shape. And you notice it looks like it's backwards. That actually is. And it's uses what's called the Zener effect, where if you reverse bias the diode, and they make them special, it will conduct in the reverse direction at a particular voltage. So you can use it as a rudimentary voltage regulator. Okay, what type of switch is represented by component three?
A.
Yeah.
What is component four?
Duh.
D.
Okay. Diodes can also be used as rectifiers because they conduct in one direction. So we can convert alternating current to pulsing or pulsating direct current. And when they're doing that, we call it rectification, and we call them rectifiers. So in this little circuit, just a half wave rectifier. So we have 100, doesn't show there. Say it's 120 volts coming in through the switch to the transformer, and we get some higher or lower voltage coming out of it. And you notice in the plot The gold line is the output or the secondary. And you see it follows the positive side of the input waveform, but it does not conduct on the negative. So you get these DC pulses, and the amplitude of that's going to be dependent on the turns ratio of that transformer. In this case, it's a step-up transformer because we're getting higher voltage out than we put in. This kind of shows how a typical transformer of the old style is constructed, where you have two windings. You can have more than two. A lot of times they'll have, especially in the old two-type radios, they would have 3, 4 windings on them, one for the filaments and one for plate voltage and one for screens to generate different supply voltages. Most of the transformers in modern electronics are going to be done on a toroid, which is a piece of ferrite like a donut, but it works the same way. It kind of constricts the magnetic flux lines within that permeable material, and it's called mutual inductance. So the current going through one winding will induce a current or voltage through the other winding due to the sharing the magnetic field. If it's a step-up transformer, it means that we have more turns on the secondary than we do on the primary, so we'll get a higher voltage out of it, but we'll also get lower current because it only transforms, there's no gain. So the power will be the same, assuming you had no losses in the transformer. In the real world, there'll be some loss in the core, so you won't get all of the power out the other side. If it's a step down, you're going to get a lower voltage out, get a higher current capability out, higher current than on the primary. If it's an isolation transformer, it means it's 1-to-1. And that's used a lot of times just to isolate ground.
Also means you have like 3 dB and lost a little bit more.
I'm not sure what the loss is. It depends on the material and things, how many windings and resist,
So
the wire itself has got resistance, so that's part of the loss.
that's actually how they get rid of the noise a lot of times, just dropping the power. The noise is a smaller
Yeah.
portion.
A lot of the audio stuff, commercial, uses 600 ohm 1-to-1 transformers and then when they get to a final speaker, it goes 600 down to 8 or 16 or whatever. Okay, what component changes 120 volt AC power to a lower AC voltage for other uses?
Wow.
B,
Right, a transformer, it transforms. Which of the following devices or circuits changes an alternating current into a varying direct current signal?
B,
What is component 6?
B,
Only one passed. But that's
What is component 8?
right. Yeah.
LED.
You don't know.
Yep.
Yeah, one black.
What is component 9?
C, hey, Robert, quick question on component 9. I see a connection going back. Is that a feedback loop back to the resistor?
You mean from the right side to the middle?
Yeah,
That's how it becomes a variable resistor. There's mechanically, there will be some sort of a wiper that slides along the resistive material. And that's what's connected to that third terminal. So
Okay.
as you move it from one end to the other, okay, it shorts out part of the resistor and allows the other. So it allows you to go from 0 ohms up to whatever the maximum value of that resistor is.
Got it.
The component 6, the capacitor, what is the curved line telling us versus, 2 parallel lines?
I don't remember. But there's a reason why they do a curved one.
Yeah,
For electrolytics, it will usually be a straight line with little feet sticking up to indicate the negative side of an electrolytic. I don't remember what the curved line means, but as far as the exam, it's a capacitor, one of many types.
you're gonna be up tonight thinking,
I'll have to look that up. Did I explain number 9?
Yeah, that's good.
Yes.
Okay.
Yeah, it's like a dimmer switching.
Okay. There's 3 of these circuits that will be may be on the exam. You're probably going to get one of them. In this one, number 2 is a variable capacitor. This time it has straight lines indicating the plates, and the arrow means that they move relative to one another and mesh. Number 3 is a variable inductor. Now, that can be similar to the variable resistor, where there's some sort of wiper that moves along the coil, or it could be physical taps where you actually move it, or it could be, of course, in this case, they're not showing a core. Most of the variable inductors I'm familiar with had a movable ferrite core in them, and you could screw it in and out, and that would affect the amount of inductance. And in some cases, they actually used a brass core because it would, for small values in inductance. And number 4 is an antenna. So what is component 3?
Indeed.
What is component 4?
Okay.
Byron's favorite. Is that an end-fed?
gotta be, it's my favorite.
Okay. Resonant or tuned circuits. They are composed of inductors and capacitors, either in series or in parallel. Will usually be called an LC circuit. And I showed 2 examples of a series and a parallel down below. If it's a series tuned circuit, it means that it will have very low impedance or resistance at the resonant frequency. If everything was perfect, it would have 0 impedance or resistance at resonant frequency. If it's a parallel circuit shown in B, it's going to look like a very high impedance at the resonant frequency. In that particular circuit, it would look like when it's resonant, it would look like it's not even there. You just have the resistor. So the resistance of that circuit, it would just be R at resonance. The little animation is showing how it resonates. And what we're doing is taking the electric field charge and the capacitor, that energy, okay, and we store it up until it's full, okay, and it's no longer passing any current. And then it collapses and charges up the inductor and creates a magnetic field and stores that same amount of energy in the inductor up to the point where it stops storing, and then that tends to collapse, and it just oscillates back and forth. When that's happening, you get the effect of zero impedance or maximum impedance, depending on whether it's series or parallel. Which of the following is a resonant or tuned circuit?
A.
Inductor or and capacitor, you have to have them both in series or parallel. Which of the following is combined with an inductor to make a resonant circuit?
D.
All right.
See.
Okay, other components. Switches are used to open and close circuits. We already saw a single pole, single throw switch. They can switch an input or output between two or more circuits. If it's a single pole double throw, or SPDT, which is shown in the diagram below, it connects a single circuit, which is the battery, between two other circuits, either the light bulb or the LED, depending on its position. So what is the function of a single pole double throw switch?
C.
Yeah, single circuit switch between one of two other circuits. Okay, a relay. It's an electrically controlled switch. It's kind of like a mechanical transistor. Okay, and I can either turn it on or turn it off by applying a current through the winding. And it causes the switch to move between one contact and the other. They can have multiple contacts, not just a single. It can be a single pole, single throw, or single pole double throw, or double pole double throw, lots of combinations. The voltage on the input, which causes current to flow through the inductor or coil part of it, will cause the relay, causes a magnetic field, which will attract the switch element, which is some metal ferrous material that's moved by the magnetic field and causes a switch from one contact to the other. I don't know why they use, in this picture I got the funny symbol for the diode in black, but okay. What is a relay?
A.
Okay, meters. They're used to display quantities as a numeric value. It can be an analog meter or a digital meter. In the analog meter, it's a little coil in there which is between some magnets, and it causes the little needle to move from one side to the other, proportional to the voltage or the current going through the meter. If it's a digital one, there's some electronics in there that converts to the digital display, which could be anything from LED numeric displays, to arrays of LEDs, to liquid crystal displays, to Nixie tubes. There's tons of, there's gas discharge type that glow orange. Haven't seen those in a long time, but those were cool. They're normally used to display output voltage of a power supply or the power of a transmitter. Just tons of other uses. I mean, it might just be on a clock display for time. It could be on a weather display for temperature. Anything you want to display. Which of the following displays an electrical quantity as a numeric value?
C.
Integrated circuits. It's a usually silicon substrate that has other semiconductors and other components, can be resistors, inductors, capacitors, combined on it. That's why it's called an integrated circuit. Usually, like I said, it's silicon. If it's like a microprocessor, it will have millions of transistors in addition to lots of little capacitors and resistors on it. They can also be both analog or digital. In the case of analog integrated circuits, one of the most common is a voltage regulator, which you use in power supplies, whether it's a linear power supply or a switching power supply to control the output voltage. In the digital, it can be not only microprocessors, but any type of digital circuits. Another one they don't talk about is for analog, it could be operational amplifiers. And there's all sorts of specialized RF circuits that are in integrated packages. What is the name of a device that combines several semiconductors and other components into a single package?
C.
What type of circuit controls the amount of voltage from a power supply?
A.
A.
Okay. Fuses. They're used to break a connection to prevent current overload. In this circuit, the fuse shown as F1 is going to hopefully prevent resistor R1 from burning up if the supply voltage became too high. And it would also help protect the supply power supply over there by stopping current flow and possibly preventing a fire. I think they get into the fire thing on the general in the question. What electrical component is used to protect other circuit components from current overloads?
I'm going to guess A because I haven't heard of the other two.
Well, we talked about varactor, but not in detail. Varactor is a special diode that's used as a variable capacitor. And a thyratron is a high power vacuum tube that's, I don't know that much about it. It's not a klystron. Maybe Vyra knows what a thyratron is.
Thought that's one of those Transformer characters on the movie Cybertron. Yeah. Megatron, Cybertron.
Okay. Anyway, correct answer is a fuse.
Yeah, the thyroid problems.
Shielded cables. They're used to prevent coupling of unwanted signals as well as radiation of signals. So it keeps the electrostatic field within that outer shield. Similar to a coaxial cable, except it's not, because they're not coaxial in this case. If there was just one and it was centered and physically constrained to be in the center, so it was equal distance to the shield, it would be a coaxial cable. And normally you connect the shield at least on one end to a ground to act as that Faraday shield. Which of the following is a reason to use shielded wire?
C.
Yeah.
Okay. You guys did really good. You'd passed the test so far.
If we could stay away.
Almost guaranteed to get 9 questions right.
All right. Well,
Any questions?
How many total questions are on the test?
35.
35.
Yeah. So we went through 9 of them. So what we went through the last couple hours, you'll get 9 of those questions that we went through.
Have you ever seen a corn-o-meter?
No.
Really? You should stay up a little bit later.
Well, I do, but I don't watch the same thing you do.
Oh.
What did he say it was?
TV show
A
shows,
cornometer?
yeah, it shows B-rated, sci-fi and horror movies.
Yeah.
And the guy tell,
What'd you say? Pornometer?
porn.
Cornometer.
And the host tells corny jokes about the movie.
Oh,
at
okay.
the breaks.
Okay.
So he's got a cornometer that's full tilt.
Ah,
Yeah.
kind of like what Elvira used to do on the mystery movies
Yeah.
with the, yeah. Okay. Any other questions?
Oh,
The main thing for the test is just go through the practice exams. It's to some people, what we went through today is some of the hardest stuff. To other people, what we're going to do, probably the last session, is the hardest stuff with rules and regulations and some operating procedures. Because those are just legislative things and sometimes they don't make sense. It's just stuff you have to memorize and remember. The band plans are another area where you just kind of have to remember it, what frequencies you're allowed to operate in and what modes. And there's some handouts I have for the people that are here. I assume I'll be seeing you guys in person again sometime.
Yeah.
Okay.
Not next week, but the following weekend, you'll see me in person.
Okay. Remind me to give you the band plan stuff. Some nice free material from the ARRL.
Okay.
Okay. No more questions?
just after we're,
Do you have any trouble with anything?
The conversions a little bit, but I think I just have to brush up on my math.
Yeah, those, a lot of people have trouble with those. You just have to practice them and get familiar with what micro and nano and pico and all that means.
Yeah, if I could associate them with the correlating power, I could just move the decimals and I'll be fine.
Okay. Remember, when you take the test, you could write anything you want on the back of the answer sheet. So any of that stuff you might have trouble remembering, just write it down as soon as you can. Do your little pie charts and other conversions. You're only likely to get one question about decibels, and it'll be a simple one, like whether it's 3 dB or 10 dB.
Mhm.
And we only went through 3 or 4 anyway, so you might get one of those. Okay, I'm going to stop the recording.